Right now, as you are watching this, there is a group of trees quietly pulling fertilizer out of thin air. Not a small amount either. Hundreds of pounds of nitrogen per acre every single year, completely free. No factory, no fossil fuels, no billion-dollar supply chain. Just sunlight, air, and bacteria. And yet governments, homeowner associations, and conservation agencies across the world are spending millions of dollars every year trying to destroy them. They have been called trash trees, weed trees, ghetto palms, and the tree of hell. You have probably seen them growing out of sidewalk cracks, abandoned lots, highway medians, and anywhere else that polite society has forgotten about. But here is the thing the labels do not tell you. The science behind these trees tells a very different story from what you have been told. The global fertilizer industry is worth hundreds of billions of dollars. These trees produce the same essential nutrient that industry sells, using nothing but the sun above them and the microbes beneath them. So, why exactly does everyone want them gone? Let us start with the trees themselves, because you need to know what we are actually talking about. First, there is Ailanthus altissima, the tree of heaven. Originally from China, it was brought to the United States in 1784, and for decades it was celebrated as a beautiful, fast-growing street tree. Today, it is called the worst invasive tree in North America. Then, there is Leucaena leucocephala, the white lead tree, native to Mexico. In the 1970s and the 1980s, international development agencies promoted it as a miracle tree because of its extraordinary nitrogen-fixing ability. Today, it sits on the list of the 100 worst invasive species on Earth. There is Albizia julibrisson, the mimosa, or Persian silk tree, a member of the legume family, native to a range stretching from Iran to Korea. It has those unmistakable pink flowers that look like something from a dream. It fixes nitrogen through root nodules, and it is considered invasive from New York to Texas. And then there is Alder, a genus that is actually native to much of the northern hemisphere. Alder fixes between 130 and 320 kilograms of nitrogen per hectare per year through symbiosis with Frankia bacteria. And yet, even alder has been classified as an environmental weed in New Zealand, despite being one of nature's most crucial pioneer species. 4 trees, 4 different origins, one shared ability that should make every gardener sit up and pay attention, and one shared reputation as something the world would be better off without. To understand why these trees matter, you need to understand what they are actually doing underground. Nitrogen fixation is the process of converting atmospheric nitrogen gas, which makes up 78% of the air you breathe, into ammonia, a form that plants can actually absorb and use. Without available nitrogen, plants cannot build proteins, cannot produce chlorophyll, cannot grow. It is the single most limiting nutrient in most ecosystems on Earth. Humans figured out how to do this industrially in 1909 with the Haber-Bosch process. It requires temperatures of 400 degrees Celsius and pressures of 200 atmospheres. It consumes between 1 and 2% of the entire world's energy supply. It is responsible for producing the synthetic fertilizer that feeds roughly 4 billion people alive today. These trees do the exact same thing at room temperature, for free, powered by nothing but sunlight. The mechanism depends on the tree. Legume-type trees like Mimosa, Leucaena, and Albizia use symbiotic rhizobia bacteria that colonize specialized structures called root nodules. It is the same biological system that operates in beans, clover, and peanuts. Actinorhizal trees like alder and casuarina use a different partner, Frankia actinobacteria, that form root nodules sometimes as large as a human fist. The numbers are staggering. Red alder delivers 130 to 320 kilograms of nitrogen per hectare per year directly into forest soils. Sitka alder adds 60 kilograms per hectare per year, and in doing so, transforms sterile glacial terrain, bare rock and gravel left behind by retreating ice, into soil capable of supporting entire conifer forests within decades. Leucaena produces foliage biomass of 2,000 to 20,000 kilograms of dried matter per hectare per year, all of it rich in nitrogen. When the leaves drop and the roots decompose, that nitrogen is released into the surrounding soil, fertilizing everything nearby. Scientists call this facilitation in ecological succession. It is the foundation upon which forests build themselves. These trees are not just growing, they are manufacturing the soil that every other plant needs to survive. So, if these trees are doing something this valuable, why is the official position of nearly every government agency, conservation organization, and urban planning department that they need to be eradicated? Because the other side of the story is real, and it is serious. Ailanthus produces up to 30,000 seeds per kilogram of fruit, all of them wind-dispersed, capable of germinating in virtually any disturbed ground. Leucaena forms dense, impenetrable thickets that crowd out all native vegetation beneath them. In Pune, India, the situation has become so extreme that 8 out of every 10 trees uprooted by wind are Leucaena, and the city is actively begging for their removal. Ailanthus does not just outcompete its neighbors by growing faster. It produces allelopathy in its roots and bark that actively poison surrounding plants through a process called allelopathy. It is chemical warfare, and the neighboring plants have no defense against it. But the deeper ecological problem is more subtle and arguably more damaging. These trees change entire ecosystems by flooding low nitrogen environments with fertility. That sounds like a good thing until you realize many native plant communities evolved specifically for lean, nutrient-poor conditions. When nitrogen suddenly becomes abundant, the species that thrive in poor soil are outcompeted by aggressive, fast-growing plants that could not survive there before. The specialized native insects and wildlife that depend on those native plants lose their food sources. Entire food webs collapse. The biodiversity that took thousands of years to develop unravels in a generation. And there are practical problems too. Ailanthus is now directly tied to the spotted lanternfly crisis sweeping the eastern United States, a devastating invasive insect that uses tree of heaven as its preferred host plant. Ailanthus roots crack building foundations, invade sewer lines, and buckle sidewalks, causing real infrastructure damage. Male Ailanthus trees produce flowers with a foul odor many people compare to rotting cashews. These are not minor complaints. But here is where the conversation usually goes wrong. We treat this as a binary. Either these trees are trash that needs to be destroyed, or they are miracles that need to be celebrated. The truth, as it almost always does, lives in the space between. Scientists who study Leucaena literally call it a conflict tree, valuable for forage production in managed systems, devastating when it spreads unchecked. The real variable is not the tree, it is context. And context changes everything. On degraded, nitrogen-poor land, these trees are ecological heroes. Actin or hazel plants are pioneer species on moraines, volcanic flows, sand dunes, and mine tailings. They are nature's original soil builders, the first organisms to arrive after catastrophe and begin the slow, essential work of creating something from nothing. In an intact native ecosystem, those same trees are destroyers of biodiversity. In a managed permaculture or agroforestry system, they can be genuine gold mines, providing free nitrogen, biomass for mulch, fodder for livestock, firewood for fuel, and even edible products. The tree did not change between those three scenarios. The context did, and this is the part that rarely gets discussed. Native trees do the same thing without the invasive risk. Alder is native across much of the northern hemisphere and fixes nitrogen at rates that rival any tropical invader. Bayberry thrives in poor sandy soils and provides nitrogen to surrounding plants. Sweet Fern colonizes disturbed ground across northeastern North America. Ceanothus species are native across the continent and fix nitrogen on dry slopes where almost nothing else will grow. These are all native nitrogen fixers that perform the same fertilizer miracle without threatening local ecosystems. And then there is Moringa oleifera, another fast-growing tree with nitrogen-rich leaves containing 9.4% protein and massive nutritional value. It is drought-resistant, extraordinarily productive, and has low invasive potential compared to the others on this list. The tools exist, we just keep reaching for the wrong ones. So what should gardeners and land managers actually do with all of this? First, do not plant known invasives in your area. Check your local invasive species lists before you put anything in the ground. The short-term benefit of free nitrogen is not worth the long-term ecological damage of an uncontrolled invasion. Second, plant native nitrogen fixers instead. Alder for wet areas, Ceanothus for dry slopes, Bayberry for poor sandy soils, and native leguminous trees and shrubs for whatever climate zone you live in. The nitrogen is just as free, and the ecological risk drops to near zero. Third, if you already have these trees on your property, consider chop and drop management. Coppice them, cut them back hard, and use the nitrogen-rich biomass as mulch around your other plants. You capture the fertility without letting the tree reproduce and spread. Here is a critical warning. Never just cut and abandon Ailanthus. It resprouts aggressively when cut, sending up dozens of new shoots from the root system that are far worse than the original tree. Cutting Ailanthus without a follow-up treatment plan, usually involving careful herbicide application to the stump, is one of the most common and most counterproductive mistakes people make. Every garden needs nitrogen. That is not optional. It is basic plant biology. The question is where that nitrogen comes from. Synthetic fertilizer from the Haber-Bosch process feeds billions of people, but it costs energy and money, and it carries environmental consequences from runoff and greenhouse gas emissions. Nitrogen-fixing trees do the same work for free, powered by sunlight and microbial partnerships that are older than any human technology. The trash label that gets slapped on these trees is not really about the trees at all. It is about human management failure. We brought them to places they did not evolve in. We planted them without understanding what they would do. We abandoned the landscapes where they took hold, and then we blame the trees. These organisms are doing exactly what nature designed them to do. They colonize disturbed ground, rebuild soil fertility, and create the conditions for more complex ecosystems to follow. They are not trash trees. They are the most sophisticated chemical factories on the planet, running a process that human industry can only replicate by burning enormous quantities of fossil fuel. The question was never whether they are valuable. The question is where you plant them and how you manage them. Get that right, and you have a free fertilizer factory that runs on sunlight. Get it wrong, and you have an ecological disaster. The tree does not care which one you choose. It will keep fixing nitrogen either way.